last lecture we have discussed about minterms, max terms, SOP, POS. Okay, let us continue with the remaining part. Let us see one question. Okay, first. Write on the question. Determine the number of Boolean functions possible. Determine the number of Boolean functions possible with n Boolean variables. With n Boolean variables. Determine the number of different Boolean functions possible with n Boolean variables. N Boolean variables. Please copy the options. 2 power n, 2 power n minus 1, 2 power n, 2 power n minus 1. So what is the answer? Answer is definitely not 2 power n. Let us see what is the answer. Here please, they are not asking the number of minterms or max terms. Minterms and max terms, you know from the previous lecture, it is 2 power n. N variables can form 2 power n combinations. That will give you 2 power n minterms, 2 power n max terms. But how many functions are possible? What is the meaning of function here? Function means by using these minterms and max terms, with the help of their combinations, we should form a function. See, for example, see. Let me take n equal to 2 variables, a and b. a, b can be 0, 0, 0, 1, 1, 0, 1, 1. Now, my function can be like this. My function, I am taking with the help of minterms or max terms. Anything you can take, I am starting with minterms. Okay. So, my function have different possibilities. Firstly, how many minterms are there? 0, 0, 0, 1, 1, 0, 1, 1, 2 power n. 4 combinations are possible, 4 minterms. Okay, let me take it as m. m is equal to 4. So, for example, I can form a function which is 0 for all the input combinations. What is y0? Which is by default 0 for all. Similarly, I can form one function which is 1 for first case, remaining all cases it is 0. And what is y1? It is 1 only here, which is nothing but minterm 0 only. What is the minterm 0? A bar, b bar. Sum of the minterm 0. Okay. Next, I can form y2, which is 1 for second case, remaining cases may 0. So what is y2? It is 1 only here. What is this? 0, 1 case. That is a bar b. Now, like this, I can form another function y3, which is 1 for first 2 cases, remaining cases may it is 0. That is, what is y3? A bar b bar plus a bar b, which is nothing but minimize it to a bar. So here, I have not selected any minterm. Here, minterm 0 is the output. Here, minterm 1. Here, minterm 0 plus minterm 1. Like that, how many possibilities are there? No minterm. 1 minterm, m0, m1, m2, m3, you can take 2 minterms, 3 minterms, you can take all the 4 minterms. So, how many combinations possible here? All zeros, no minterm to all ones. That is, you can have a function y15, y means output of a function, okay. So, all zeros to all ones. So, what is this function y15, which is equal to sum of all the minterms, which will give me 1. So, no minterm to all minterms. So, all zeros in the output to all ones. 4 zeros to 4 ones. So how many different functions are possible? y0 to y15, total 16. Or 4 zeros to 4 ones means 2 power 4, 16 functions are possible. Here, how I got this 4? Because the number of minterms is 4. How many minterms formula is 2 power, here n. What is n here? Because n is 2, 2 power 2 is 4, I got this. So can I say here 2 power 4 place mein 4 is nothing but number of minterms here. So 2 power m, right? Now what is m? M is nothing but 2 power 2, or you can say m is nothing but 2 power n. So with n variables, how many different Boolean functions are possible? You can make 2 power n. If n is 2, 2 power 2, 16 is the answer. If n is 3, 2 power 3, 2 power 8 is the answer. Like that, 256 something you will get. Like that, with increase in the n, you will get 2 power n is the answer. Copy it. Okay, the next one, let us take one question based on this. F of A, B, C is equal to F of A bar, B bar, C bar. What is the condition? F of A, B, C equal to F of A bar, B bar, C bar. Determine the number of different functions possible. Determine the number of different functions possible. F of ABC equal to F of A bar, B bar, C bar. Determine the number of different functions possible. You can understand here. F of ABC, A bar, B bar, C bar, both are same. Like this, how many functions you can form? That is the question. Use that previous knowledge, you can do this very easily. Say for example, A, B, C. They can be all zeros to all ones. What is the meaning of F of ABC equal to F of A bar, B bar, C bar? You understand here. Suppose your F of ABC is 0, 0, 0. Then what is A bar, B bar, C bar? 1, 1, 1. If it is 0, 0, 1, then it will be 1, 1, 0. If it is 0, 1, 0, it is 1, 0, 1. If it is 0, 1, 1, this is the mapping required. Or you can understand, the function should have same output for 0 and 7. Function should have same output for 1 and 6. Same output for 2 and 5. Same output for 3 and 4. Then we can say it is satisfying that particular condition. Is it clear? The function F of ABC. ABC can be all zeros to all ones you can take. See, you can understand, if it is 0, 0, 0, F of ABC is F of 0, 0, 0 must be same as F of 1, 1, 1. Say your answer is, for example, 0 here. Answer here should also be 0. Your answer is, say your function is 0 here, it should be 0 here. If your function is 1 here, it should be 1 here. Or you can say your function is x here. Function is, output is x. X can be 0 or 1. Same x should come here. Say your output is y here. The same y should come here. Y can be 0 or 1. If your output is z here, same z should come here. Your output is w here, same w should come here. So you can understand here, previously I have the possibility of all zeros to all ones. Now I don't have all choices. I have only this choice. This choice will decide the second part. Or you can say total number of choices is reduced to half. Here 2 power n is my answer, which is m. This is m by 2. This is m by 2. Okay. Or you can understand first half and second half are satisfying one particular condition. Whatever we have like this, same you should have like this. Then only this function will be satisfied. So these can be any value. They can be all zeros to all ones. Accordingly, you will get the output in this 4. Right? Say f of ABC means your ABC can be any value. Then the function should have same value for A bar, B bar, C bar also. So here, these 4 and these 4, they can be anything. They can be all zeros to all ones. Here also all zeros to all ones. So now you can understand how many combinations I can form. 4 zeros to 4 ones, 2 power 4. Okay. Or you can understand how many functions I can form. 16. Or you can take the answer like this, 2 power m by 2. But what is m? 2 power n. So 2 power m is equal to this. Then what is m by 2? 2 power n by 2, which is 2 power n minus 1. So m by 2 can be replaced by 2 power n minus 1. This is the answer generally for that condition. You can use this as a hint for solving the question I have given in the basics, that is the number of self-dual expressions. Similar logic, not same logic, similar logic we can apply for finding the number of self-dual expressions possible in a particular number of variables. Okay, for example, you have 3 variable or 4 variable, any number of variables. How many self-dual expressions are, how many self-dual functions are possible? In the basics, I have given the formula. What is the answer formula I have given? 2 power n minus 1. Same answer we got it. Similar logic, whatever we have done, not the same, but small change will be there. You can understand here. Function is the same as functions dual. That is the condition required. Okay. Using this, okay, suppose how to get function dual? All zeros will be replaced by all ones at both input and output. Then you will get a function dual. For example, see here. It is my function. In the function dual, it should be 1 1 1 0 0 1 0 0 we take. Okay. You take here some output function, here some output function. Both the cases my answer should be same. That is, you can understand here. If you have x here, I should have x here. Say if you have something here, I should get same something here. Okay. You can understand here. Please understand. Let us take here also. Let this will be w, x, y, z. Okay. In the function dual, what will you get? W bar, x bar, y bar, z bar. Now, what is the condition required for making the function as self-dual? Here, the 1 1 is having the output of z, na? So w bar should be equal to z. Then here 1 0 is having the output, so y, that is x bar should be same as y. Okay. Then y bar is equal to x and z bar is equal to, what is z bar? W. Or indirectly, here y should be equal to how much? X bar. Z should be equal to z is equal to how much? W bar is the condition required. So here first half is defining second half, but it is not in the same order. In this case, it will be complement. Then we can say the function will be self-dual. Okay. For clear understanding, easy way to understand, let us take one example. AB is equal to F 0 0 0 1 1 0 1 1. Let me take randomly this answer. Whether it is self-dual or not, let me check it. Apply duality property. Then AB will be, what is the duality property? All zeros will be replaced with all ones. All ones will be replaced with zeros. Now let me check whether this function is self-dual or not. In the original function, 0 0 is giving me 1. In the dual, 0 0 is giving me 1. Okay. In this, 0 1 is giving me 1. Here also 0 1 is giving me 1. Here 1 0 is giving me 0. Here also 1 0 is giving me 0. 1 1 is giving me 0 here. Here also 1 1 is giving me 0. So it is a self-dual. Suppose I change this. Now 0 0 1. Okay, 1 1 0. 1 0 0. 0 1 0 1. Here 1 1 1 means the 0 0 will come. Now is it self-dual? No. Here original function mein 0 0 is 1. In the dual it is 0 0 is 0. So it is not self-dual. So here you can understand self-dual condition is like this. The top part and the bottom part, if you read like this and like this, so this part should be complement of this part. then only we can say it is a self-dual. That is what I derived here. Here wx, here w bar x bar should come. Then we can say the function is a self-dual function. Here whatever you have, wx can be anything. They can be 0, 0, 0, 1, 1, 0, 1, 1. But total number of combinations is reduced to half or not, because first half is deciding second half. So for me, how many possibilities are there for w and x? Only your answer here, wx can be 0, 0, 0, 1, 1, 0, 1, 1, or only 2 power 2, which is 4, or you can say same as previous case, 2 power m by 2 or 2 power n minus 1. That is how we derive the number of self-dual. Earlier I have given this as a homework. Now you can find the solution for this. Okay, is it clear? What I am saying is, if you have all the 8 is free for you, you can select all the 8 can be anything. There is no logic like this. Then they can be all zeros to all ones. We have 2 power n. But here there is a condition. What is the condition given by examiner? ABC condition should be same as A bar, B bar, C bar. So that should be satisfied. First half and second half, like this and like this, they must be same. If they are complement, then what we get it is called self-dual function. Both are similar but not same. Okay, copy it. Your question is complete here. Okay, this is for self-dual. Okay, that is about your min terms, max terms, SOP, POS conditions and some problems based on this. Okay, now let us discuss with your next part, that is K-map, Carnot map. Another name for this is which diagram. Right. Earlier we have discussed self-dual expression. Okay. Similarly, Boolean algebra also we have explained. Okay, we have done some questions based on Boolean algebra, but the problem with Boolean algebra is sometimes you may end up with confusion, or it may be taking more time if the equation is complex or number of variables are more. When you have less number of variables, it is okay. When you have more number of variables, it will be difficult to solve by Boolean algebra. And whenever we have more number of variables, then to simplify the logical expressions, we take the help of K-map. That is the ultimate aim of K-map. Write down K-map, keep the heading K-map, write down. K-map is used for minimization of logical expressions. K-map is used for minimization of logical expressions when we have more number of variables, and the variable can be, when we have more number of variables and the variable can be either 0, 1, variable can be either 0, 1 or don't care. What is don't care? I will explain. Okay. In the Boolean algebra, your variable can be only either 0 or 1. Here new condition is don't care. We represent with X. Don't care means it can be 0 or 1. What is the condition for don't care? We will discuss that. Okay. Just for continuity, write down. What is that? K-map is used for minimization when we have more number of variables and the variable can be either 0, 1 or don't care. Okay. Before going to K-map, let us have a small basic about our binary number representation. In the binary representation, A and B are I am having A and B. AB can be 0, 0, 0, 1, 1, 0, 1, 1. Okay. 0, 0 means A bar, B bar. 0, 1 means A bar, B. You can understand if we add these two. Okay. 0, 0 meaning what? A bar into B bar. A bar into B. If you add these two, what is the answer? A bar is the answer. Yes or no? A bar, B bar plus A bar, B. What is the answer? A bar. Can I take anything common here? A bar, B plus A, B bar. You cannot take anything common. Here 1, 0 and 1, 1 may. Yes, you can take common. A, B bar plus A, B. What is the answer? A. For last and first, you cannot take anything common. So here, you should observe one important point. When I am able to take common, say for example, between 0, 0, 0, 1, we have taken 0 common and 0 plus 1 we have neglected indirectly. 0 means here A bar is taken common, B bar plus B is 1 we have neglected. That is 0 is taken common, 0 plus 1 is neglected. So here there is nothing to take common, but here also I can take common. What is common? 1. When 1 is common, you can neglect this 0 plus 1. So every time we can eliminate 0 plus 1 in this representation. Now I change a small, I am going by another way called gray code. Okay, this is called gray code. Here, one important observation, let us see. Here, between the first and the next, what is the, we can take common, what is the bit we can take common? 0 is, we can take common, 0 is taken common, A bar. Between these two, 1 can be taken common, B. Between these two, this one can be taken common, A. And first and last, 0 0 1 0 mein you can take this 0 common, and what is the answer? B bar. So you observe here. What is the difference between the first code and second code? This code you observe here, why I am able to take common, because only one bit has changed. Why I am not able to take common? You observe this 1 changed to 0, 0 changed to 1, both the bits are changed. So both the bits are different, you cannot take anything common. If at least one bit is same, you can take common. You observe here, 0 0 0 1, only one bit has changed. 0 1 1 1, this bit is same, only this bit is changed. 1 1 1 0, this 1 is the same, only this bit is changed. And 1 0 and 0 0, that is last and first, you can observe this 0 is common, only this bit is changed. Here, this is also called as cyclic unit distance code. Cyclic, why cyclic means from last to first we have this unit distance property. Okay, cyclic unit distance code, because between any two adjacent we have one bit distance. Distance means one bit is changing here, one bit, only one bit is changing between any two adjacent numbers. It is also called as adjacency property. Between any two adjacent numbers, only one bit is being changed. It is a cyclic unit distance code, because from last to first also we have this property of unit distance code. So cyclic unit distance code is the property of gray code. It is a cyclic unit distance code, or we can also call it as adjacency property. Between any two adjacent numbers we have only one bit difference. Because of this, we use this in your K-map. Gray code is being used in the K-map. So that's why in the K-map, I will show you, we don't use the pattern 0 0 0 1 1 0 1 1. We use the pattern 0 0 0 1 1 1 1 0 pattern. Okay. This is the basic for that. First copy this part. Okay, write down. Because of the adjacency property, gray code is used in K-maps. Gray code is used in K-maps. Gray code is used in K-maps. Okay. Now let us see the procedure for the K-map. First point. See here, I am going by SOP method. First we are discussing for SOP. Later we will discuss for PYS also. Both the rules are almost same. Just here min terms, there max terms. That is the only difference. Okay. So keep the side heading procedure. First point. Always give priority. Always give priority for grouping of maximum possible adjacent cells. Always give priority for grouping of maximum possible adjacent cells. Here this is the possibilities we will be having. First one, octet. Okay, what is the meaning of octet? A group of 8 adjacent cells. Okay, next priority, quad. Quad is a group of 4 adjacent cells. Next priority, pair. It is a group of 2 adjacent cells. Lastly, single term. It is nothing but your min term or max term. So whenever you form a K-map, these are the rules in this first point. What is the first point? Always go for the priorities. Give priority for grouping of maximum possible adjacent cells. First case we can say first priority should be given to, if total K-map is available for grouping, the answer will be either 1 or 0. Okay. Otherwise generally octet. Octet means group of 8 adjacent cells. Quad. Quad is a group of 4 adjacent cells. Next priority is pair. Pair not possible, take single terms. This is the priority we should go. 8, 4, 2, 1. Okay. You may have the doubt, sir, can I make 3 as a group? Generally, with respect to minimization, in the K-map I will show you, it is not possible. 3 should be taken as again 2 pairs. 3 cells side by side. Can I form as a group, sir? These are the only groupings possible. If you have 3, we should take it as 2 pairs. I will show you when we discuss about with the figure. Okay. So this is the priority. Please copy this. Okay. Second point. Each min term brackets write down max term if it is POS, bracket close. Each minterm must be covered at least once. Then only your function is completely covered. When you write the expression, we should take care of all minterms. You should not leave any minterm. If it is SOP, if it is POS, we should take all max terms. Okay. So take this second point. Each minterm must be covered at least once. Lastly, remove redundant groupings. If any group, means a pair or quad or any term, is covered more than once, okay, it is giving redundancy, means the same, suppose it is already covered, if you take extra, it will not give you minimized answer. What is our ultimate aim in the K-map? We want to minimize the expression. That is the reason why we are going for combining maximum possible cells will give you minimized expression always. Okay. So after every term is covered or not, we should check. After that, what we need to do? Remove if anything we have covered twice. Okay, I will show you. There is a, with the help of example, if a particular pair or quad is already covered by some other pair or quad, okay, then we can neglect that. We should not take, say for example, like consensus, like your expression is like this. My expression in the K-map should be like this only. Whatever redundant terms are present, that should not come in my final expression. That should be identified in the K-map. I will show you how to identify the redundant groups in the K-map. So these are the three rules for your K-map. What is the first? Always give priority for grouping of maximum possible adjacent cells like this. Okay. Next, every minterm, if it is, first we try all by SOP, then I will give for POS. Okay. Simple logic, SOP mein whatever we discuss for minterms, that is valid for max terms in the POS. All minterms should be covered because total function should be covered. We should remove any redundant grouping. These are the rules of your K-map. Okay. In the next lecture, we discuss about the, we'll take the 2 variable, 3 variable, 4 variable, 5 variable, up to 6 variable K-map examples and we'll solve the problems on it. Thank you.